I am Anil Kumar. Welcome to my series on vectors. We'll discuss intersection of lines and planes in this particular video. Here, our focus will mainly be on intersection of planes. The question here is, determine the nature of intersection, if any, between all the planes listed in each of the following. Also provide a geometrical interpretation of each system. Do not solve the system. So we have four different systems here to consider. One by one, we'll look into these. So the very first one here, we have three sets of planes. We need to figure out how do they intersect. Do they intersect or not, right? So likewise, we have four of them, A, B, C, and D. I would like you to pause this particular video, copy the questions, try them out, and then look into my suggestions. The concept here will be to analyze the normals. So these equations are given to us in Cartesian forms of the form of ax plus by plus cz equals to some parameter, let's say d here. In that case, the normal is given by a, b, and c. So we'll analyze normal to figure out how the planes are going to intersect. So there'll be basically 2 points to look into. The first point will be, do we have parallel planes? All right, so if we have parallel planes, those will not intersect. And the second one is whether the normals are in the same plane or not. So that we do with the scalar triple product. So we'll do n1 dot n2 times n3, right, times cross product. So this is the scalar triple product which we are going to analyze. From this, we'll come to know exactly how the planes are going to intersect. So let's take examples one by one. The very first one, as I was saying, is the process which we are going to follow. And the process here is we'll analyze the normals, right? So we have three planes. So we have three normals, n1, n2, and n3. And in case the normals are scalar products, let's say n1 is k times n2, then we have parallel planes. Correct? That is one thing. The second thing is if the scalar product n1 dot n2 times cross product, that is equal to 0, or it is not equal to 0. So there could be two conditions, right? Or it is not equal to 0. So if it is equal to 0, in that case, what happens? And if it is not equal to 0, then what happens? Well, if it is not equal to 0, then we know that this particular condition will give us intersection at a point. However, if it is equal to 0, then we could have two scenarios. One of them could be intersection in a line, and the other could be kind of we have inconsistent system. Well, these two are consistent. Consistent means that they all intersect either at a point or in a line, right? So this is consistent, and inconsistent means all do not intersect, right? So the other condition could be that we have a prism. So they intersect like a prism. we'll actually see this condition also. Perfect. So now let's take these examples and then we'll further elaborate on the same. So in the very first example, we have three planes. Let's write down the normals first. So normal here is 2, 1, 1, right? That is the first normal. The second one is 1, 1, and 1. And the third one is 1, 0, and 1. So these are the three normals. Clearly, they are not parallel, right? So none of them is parallel. So it seems not parallel. So what we should do? Let's find the scalar triple product, which is n1 dot n2 cross n3. So we'll just do the scalar triple product and check our result. So let's do it in a different ink here. So we have 2, 1, 1. So I'll use, yeah, okay. So 1, 1, 1, 1, 0, 1. So that gives you what? 2 times 1 times 1 minus 0 minus 1 times 1 minus 1, and then we get this 1 time 0 minus 1, and that is equal to 2 times 1, which is 2, that is 0, right? So we write plus or minus 0. Here we have 1 times minus 1, which is minus 1, and what we get here is 2 minus 1, which is 1, which is not equal to 0, right? So we know this particular case is a case where the intersection is a point, right? So we have intersection is a point. So that is the answer for the first one. So we need to illustrate that. So, you could think about two planes intersecting in a particular line. Let's say, let's make it here. One plane, the other plane, two planes will always intersect in a line, right? So we can draw like this. Right? The third plane, you could think about going into this, right? So, for example, it could be drawn as if it is going into this, right? So, kind of like this. So, we have a point of intersection as being shown here. Is that clear to you? So, that is how it is going to be. Now, let's analyze the second condition. I hope this point is absolutely clear. So, what we found here is that scalar triple product is not equal to 0. So we'll say we can write this is not equal to 0, and therefore we have point as an intersection. So if you solve this, you'll definitely get a point. Okay. The next one here is, let's write down the scalar triple product straight away since we have very less space to work with. So, and then we'll analyze. Okay, now here it is 1, 1, 1. 1, and this is 0 and 1, and then we have 2, and this is 1, and that is 2. It looks very similar, right? Okay, so 1 time 0 minus 1 minus 1 time 2 minus 2, and this gives me 1 time 1 minus 0. So that is equal to minus 1. This gives me 0 plus 0, and this gives me plus 1, and which is equal to 0. Now, since this is 0, so we get this particular condition that n1 dot n2 cross N3 is equal to 0. So in this particular case, we have intersection of as a line. So line is a solution. And what is the geometric interpretation? So remember, when we are solving this question, the question here is also provide geometric interpretation of each system. Is that clear to you? So that is why we are interested in really providing this example. So in this particular case, think like this. Again, we'll take three planes. Let's say this is one of our plane. The other one, let's say this is the other one. So it intersects in a line. Okay, so that intersects in the line. So third one also goes through the same line, right? Do you see that part? So that is how you would actually sketch it. That should be a dotted line. But the idea is that we have intersection of a line, and that is the case. Is that clear to you? So what we have considered here is a very simple thing, and that is we just calculated scalar triple products, right? It was very important. If it is not equal to 0, we are getting a point of intersection. But if it is equal to 0, right, then we are getting a line of intersection. Also important thing is, in this case, not parallel, non-parallel. Therefore, all are intersecting at a point or a line in the case. Perfect. Now, let's move on and take the last two examples. So here we have the planes. We can go directly also with the dot product, but let's analyze this. Okay, either way. So let's go for dot product. So we have the normals, which is 1, and here we have 5, then we have minus 3, then we have minus 2, 7 and minus 4, and here we have 6, 30 and minus 18. Well, these are the normals, right? So this is n1, this is n2, and this is n3. These are the normals. Do you notice something in this? Well, we do have a scalar multiple here. So if you see this particular normal n1 to n3, it is times 6. So you could actually write down that the normal n3 is scalar multiple 6 times n1, right? So that means the planes pi 1 is parallel to the plane pi 3. So we have two parallel planes. Is that clear to you? So we have two parallel planes. Now how about the third one? Well, the third one, why they are parallel? Because if I multiply by 6, then we get 24, and which is not matching, right? So these values are not matching. Distance from the origin is not matching. So therefore, they are parallel planes. So in this particular case, what we have is that we have two parallel planes. They are never going to intersect. So we could draw these planes as something like this. Okay, I could have drawn like this, but the third plane will intersect them. So if I have the third plane, which is kind of like this, right? In that case, the third plane intersects these planes at different lines. Do you get the idea, right? But the system is inconsistent. That is very important to understand, right? So in this particular case, we have inconsistent system where two parallel planes are there, and the third plane will intersect them in a line as shown here. Now let's look into the next example, which is, let's write down the normals here. 1, 5 and minus 3. The other one is minus 2, 7, minus 4. And then we have 3, minus 2, 1. Right? So these are, we can actually find the scalar triple product also. But before going over there, let's analyze these normals. So are they parallel? Well, there is something very interesting about these, and it is that if I add these two, then I get the third one, right? So rather, if this is n1, this is n2, and that is n3, in that case, you will see that if I do n3, rather n1 minus n3, then I get n2. So we get a scalar combination here, right? So we do get some combination here. And then let us also analyze what happens to the scalar triple product. So we'll actually calculate the scalar triple product and get back to where we were. So let me write down. So it is 1, 5, minus 3. And here we get minus 2, 7, minus 4. Here we get 3, minus 2, 1. So we get 1 time 7, and that is plus minus 8, minus 5 times minus 2 times this is minus 2, and when you multiply this you get plus 12, and minus 3 times minus 2 will give me 4 minus 21. Okay, so 7 minus 8 is minus 1. Then we have minus 5 times 10, and here we have minus 3 times minus, this is 17. Okay, so that gives us 1 minus 50, and this is plus 51. This is minus 1, sorry, and that is plus 51. And so what we get here is 0. So in this case, we do get the condition n1 dot n2 cross n3, this is very critical, is equal to 0. Perfect. Now, as I was saying in the very beginning, when we have the scalar triple product as 0, there are two conditions. We have seen when they intersect. Now, this is the condition for the prism. How could you make it out? Because you have this linear combination which I was talking about, which is that if I combine these two, I get the third one, right? So what I'm observing here is that n1 minus n3 is equal to n2. So that forms a prism with this particular condition, correct? So how will it look like? Let me show you that also geometrically. How is it going to look like? So in this case, what we see is that the prism, the intersection is kind of like this. So you see this kind of a prism being formed by the intersection. So what I'm trying to say here is this is one of our planes, then the other plane, which is kind of like this, and the third line I will draw with the third plane. So one intersection of a plane, second intersection of the plane, and the third intersection of the plane. But what is important here is to see that they form a prism. All do not intersect at the same line, but these are different lines. Two planes intersect in a line and they don't match with the other set of intersection. Correct? So that is what it is, and it makes a prism, as I was saying. Correct? So I hope that makes sense. So we have four different types of examples here. This is the page where we're talking about inconsistent solutions. Right? Where all the three planes are not intersecting in the line or a point. And in the previous case, we had two, where one is intersecting at a point, the other one is intersecting in a line. Perfect? So these four examples are good examples to illustrate how the planes intersect. I hope you got the concept. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.